So, welcome you back again in AFM part 2. The most important part of AFM, you can consider the specimen holder or sample holder also. The sample holder should be chemically inert, easily modifiable as per the need of sample, easy to handle. If you will see the classification of sample holder, mica specimen holders, they are very popular. They are extremely smooth on its surface. Very few angstrom surface roughness is present, and these holders are quite cheap and easy to prepare also. Second class of sample holder, the gold specimen holder. Usually they are costlier in comparison of mica specimen holder, used as a thin film, preferred due to its remarkably inertness, because gold is known for its inertness. These sample holders are prepared by gold vapor deposition on mica surface. Third is silicone specimen holder. The silicone is also quite inert in nature. These holders are manufactured by using silanes. The major drawback is its poor reproducibility due to high sensitivity against water. Fourth is the hydrogen passivized silicone specimen holders. These sample holders are remarkably flat. Enough possibility of easy modification is also present there. So this class, you can see the recent class which has been added in sample holder of AFM. If you will compare the AFM with the other analytical techniques like TEM and SEM, the major feature of AFM is surface topography and similar to SEM. TEM is different here. TEM is used to get crystalline lamellar structure and other morphological fine structures. If you will see the scanning range, then you will find 0.2 nanometer to 10 micrometer AFM has its scanning range. In case of TEM, it starts from 10 nanometer to 100 micron, and SEM 0.2 nanometer to 10 micron. Effective magnification of AFM, that is 3000 to 2.5 lakh, and TEM again 3000 to 2.5 lakh, and SEM 20 to 1.5 lakh nanometer. Best resolution in AFM, that is obtained up to at 0.3 nanometer, in case of TEM 0.2 nanometer, and in case of SEM at 4 nanometer. Radiation effect, AFM is super because there is no use of any kind of radiation, so no radiation effect is there. In case of TEM, severe radiation effect is possible, and in case of SEM, almost safe because lot of changes has been made by manufacturers to make the machine safe. Specimen preparation for AFM is quite easy, but if you will see the specimen preparation for TEM, that is very tedious and time consuming, and for SEM moderate time is required, and nowadays the sample preparation for SEM is quite easy. If you will see the image detection process in case of AFM, quality of probe tip that decides the quality of image. Blunt tip and split tip, they can't give the good quality image. So tip get blunts due to the application of high level of force. And how can we identify the condition of tip? The exact typical image that will compare with the ideal image of that particular material. By comparison, we can find the quality of tip. The other situation of tip damage is to split of tip into two or more parts, and again it is verified by the present or typical picture or typical figure by comparing with ideal figure. So if you are seeing here, laser diode is here, and this is the cantilever, this is the tip, this is sample. So laser is incident here, and that is reflecting as per the position of tip, and that is captured by photo detector. The merits and demerits of AFM, it is able to scan non-conducting surfaces without making it conductive as it needed in SEM and TEM. So there is no need to prepare the sample and to coat a conductive layer on sample surface. High resolution images are produced by keeping lateral resolution of few nanometer and vertical resolution less than 1 nanometer. Produced resolution up to 0.3 nanometer is possible, which is higher than SEM. AFM successfully produces three-dimensional images of polymeric surfaces structure directly, which is not possible even in TEM and SEM. And the quality of images, particularly for surface profile, we can get best images by AFM. So the comparison of polymeric surfaces is possible by opting lateral force and phase contrast mode. Possibility of sample damage by radiation is negligible, and the tip force that can damage the sample surface only in very rare situation. By making a modification in probe tip by ferromagnetism, the detection of stray magnetic field and magnetic domain structure of sample become easily possible. Apart from all these merits, there are some demerits. Soft sample may damage in contact mode. So soft samples are advised to scan in non-contact mode. Sample contamination is also possible, and instrumentation control influences the result. So best instrumentation control is required, and the machines should be calibrated time to time to maintain the quality of images. Scope of AFM application: surface profile scanning of every class of material, conductive and optical behavior does not influence the AFM results. Vacuum is not essential in AFM, but if manufacturer advised to use the AFM under vacuum, the quality of picture that improves. The specimen size and its height remains a point of concern, which depends on volume available to mount the specimen in sample chamber of AFM. If sample chamber is small, then we can't mount a big size of sample. So we have to prepare the sample accordingly. When the specimen is kept under the measuring tip of AFM, it directed to come close to the sample measuring surface, which is similar to focusing, adjusting exercise on a optical microscope. Results in contact mode. Height data. The magnitude of z-axis on XYZ scanning piezo tube is estimated by the vertical position of probe tip. Input voltage to the scanning piezo tube is proportional to the length of the tube. The change in the z-axis magnitude is drafted as a function of topographical image of the sample surface in which height data are recorded. Phase data measures the alteration in phase angle with respect the phase offset of the oscillating cantilever. The phase offset between the two signals is defined as 0 for the cantilever oscillating freely in air. When probe tip makes contact with the specimen surface, cantilever phase offset detects by a small angle with respect to input drive signal offset. Amplitude data. The photodiode detector is capable to monitor the amplitude data. Signal to noise ratio SNR of pixel for a laser beam profile is defined as the mean value of the pixel which are divided by its root mean square RMS value. The RMS of the laser signal on the y-axis of the detector is recorded for each of the 512 segments on a given raster of the probe tip. These values of y-coordinate magnitude are arranged in the form of amplitude map of the sample surface. The amplitude images surface image remains very well. Various applications of AFM can be categorized in three classes: material topography, ceramic, coatings, composite, glasses, metals, polymers, semiconductor, and thin and thick film coated material can be easily detected or scanned by means of AFM. Phenomenal study is also possible. Phenomenal studies like abrasion phenomena, corrosion phenomena, etching, friction, lubrication, pleating, polishing, writing at very fine level. So these phenomena can be mapped, scanned by AFM easily. At atomic level, imaging of atomic resolution is also possible. Force at piconewton level is applied in case of scaffold detection or scaffold mapping. Tissue growth, atomic signature can also be possible to identify by the application of AFM. Various application of AFM: assessment of mechanical properties of thin polymer film, phase imaging, chemical mapping, evaluation of elastic properties, prediction of polymer surface aging, Nanoscale mapping of mechanical properties and characterization of various biosamples are also possible. If you will see the various AFM images of textile surfaces, here you can just compare untreated cotton fiber. The surface is visible. These are the same images, but when you will compare the same thing on AFM images, you can quantify the roughness very easily because you have X, Y and Z axis data, which are not possible in case of same images. Now the treated sample, the cotton is treated, the roughness has increased. That is visible in case of SAM, but not quantifiable, which is easily quantifiable in case of AFM. Again, the treated cotton by other resin, the quantity of roughness can be easily detected. These are the images of another treated cotton sample where the roughness is widespread and magnitude is different, which is also possible, which is also visible in case of SAM, but quantification is not possible, which is easily quantifiable by means of AFM. At innovation modifications, at latest innovation has been made in the field of AFM by replacing the conventional laser diode by helium neon laser integrated diode to the AFM head with the help of signal mode optical fiber cable to suppress the non-thermal disturbances which influences the stability of laser diodes. The Fourier analyzer is used to detect the noise power spectra precisely. We will see the conclusion. The AFM is useful in soft material like biopolymers, living cells, porous scaffolds. It is possible to integrate accessories with AFM to characterize chemical, physical, mechanical and thermal behavior of nano composites by surface profile scanning. So different type of other accessories or other equipment, they can also be integrated with AFM. In this way, the field of application of AFM that enhances 2 byte. It is capable to draw adhesion map of a sample surface also. The crystalline and amorphous phase identification is also possible. Latest innovation in electronics and material has assisted AFM to make it able to apply for biosensors, nano electronics and nano medicine characterization. To observe the action of various forces of bioconjugate genus without any alteration in physiological solution, because it is known that the electrical, mechanical, optical behavior of nanostructured assemblies primarily governed by molecular attachment, quantum mechanics, which can be easily identified by means of AFM. By significant increase in AFM responsiveness, the minute interactive forces can be detected. By depth study of strength mechanism of consideration, the combination of AFM with optical microscope will further enhance the potential of this promising analytical tool to acknowledge ligands and receptors by the application of bioconjugated AFM tips. These tips are also capable to identify the structural and functional properties of nanoparticles, nanofibers. Some other research groups have tried to measure the liquid viscosity by the integration and application of torsion rod or torsion mechanism in AFM cantilever like a whisker tip. AFM can be used in force lithography, dip and non-lithography by using that tip radius 10 to 100 nanometer range. It can be measured the non-oxidation to alter the metallic, polymeric and semiconductor sample surface either physically or chemically. AFM can be used to molecular writing on specimen surfaces where molecular chains exit from AFM tip to print a 3-dimensional desired pattern. So in this way, I am very thankful to all of you because you listened patiently. If you have any question, directly you can write me. And meanwhile, institute is going to prepare for examination. So any student who have back paper, they can contact to Mr. Ajay Pandey. He is making all arrangements related to that. So thank you very much.